All right, Mr. Chester, we are up and recording. So you should have out your notes from yesterday for Unit 3 so that you can follow along and add information. Does not have to be 2 column notes, however you prefer taking notes. And remember, it might not be chronological, so Mr. Chester might go back today and discuss in more detail about chemical changes. So I would put that next to where I talked yesterday about chemical changes so that next week when we're gone and you have an assignment, you can quickly find the information that you need to do your assignments.
Okay, quick recap. Develop models that describe the atomic composition of simple molecules and extended structures. Can you do that yet based on what I've taught? Maybe? So we've talked about molecular structures yet so far?
No.
We talked about the atom, but we haven't gotten to molecular structure. So you now know some things about the atom, and you should now know a little bit about chemical bonds. We'll make sure and talk about that some more today if we haven't talked about that. We got a little bit further in 6th and 7th yesterday. So be listening for that. Analyze, interpret data and on the properties of substances before and after the substances interact. Determine if a chemical reaction has occurred. Okay, nuclear reaction involves what? Everybody. Nuclear reaction involves the nucleus. Chemical reaction involves electrons. Physical reaction involves none of that stuff. Doesn't affect molecules or anything, okay? You're maybe not quite there, but you now know some stuff about what the difference in those things is. We're going to skip this one because we won't do it probably this time. Develop a model that predicts and describes changes in particle motion, temperature, and state of a pure substance when thermal energy is added or removed. Did we even get to states yesterday? No.
Yes.
At the very end?
States of matter.
States of matter?
Yeah.
We'll be talking about that today. Develop and use a model to describe how the total number of atoms does not change in a chemical reaction and thus mass is conserved. We have not quite done that yet, but we will talk about stuff today that touches on that. Number 6 is probably one you're going to do in the next unit, so we're going to skip to it on. Just wanted a quick refresher on that.
Just a question.
Yeah.
You said the reason we can't just plug in fluid tables electric.
Oh! Yeah, that reminds me of something. You should find something right. Go ahead.
If let's say the electrons were there, would it just be something right through? Would it be like a weird water world?
So hold that question for a minute, okay? Hold that question for a minute. Well, we'll look at this. There was a great NPR story I saw yesterday that talked exactly about what you just asked, but not about if the electrons were not there. In a minute, you should be able to give me that answer yourself. Just a second. Let's see. Oh, they didn't do an actual radio story on it. But I saw this yesterday on Facebook. And I went, hey, that's what we've been discussing. And it goes into discussing this exact stuff that we were talking about. The fact that atoms are mostly empty space and what's happening and what happens with the electrons. So I thought it was just kind of interestingly coincidental. Okay, hold that thought, and after we talk for a few minutes, see if you can tell me the answer to your own question. Okay? So we talked about this, we talked about this, we talked about this, right?
Yeah.
Did we talk about this?
Yes.
So what's this?
It's the splitting of the fission of an atom.
That's the fission of an
It's
atom.
like, it's splitting off and
Haven't talked about this enough, clearly. What kind of atom is this?
Hydrogen.
How do you know?
Because there's one.
How about this one?
Hydrogen.
Because
There's one.
how come we call these deuterium and tritium? Neutrons. Now, they're really forms of hydrogen, okay? And usually we call atoms that have different numbers of nuclei different isotopes. So deuterium and tritium are different isotopes of hydrogen. We don't real frequently give a special name to each isotope, okay? There's U-235 and U-236 and U-238, which are versions of uranium. But that just means the uranium with this particular mass, or this. That's different numbers of neutrons in the uranium. Because if it had a different number of protons, would it still be uranium? No. Deuterium and tritium are commonly called heavy water. Or make up something called heavy water. Why would it be called heavy water? What does hydrogen go into pretty frequently? H2O. So if some of those H's have an extra neutron or two, then the water is what compared with regular water? Heavier, denser, right? Denser for the same volume. So these things are typically found in the sun. This reaction is being shown in the sun. These deuterium and tritium atoms, the nuclei, the electrons are gone, but it's still hydrogen, right?
Right.
Because it's not based on the electrons, it's based on the protons. They're getting jammed together. This is the opposite of fission. Fission means to split. So this is what? Fusion. Okay? The bombs we make today are called hydrogen bombs because they're using versions of hydrogen, and they use fusion reactions. So the nukes we make today are way worse, or way larger, and much higher what's called yield, meaning much more of the material inside them actually goes off. And fission bomb, less. When these get jammed together, is this hydrogen now?
No.
What is it?
Helium.
Helium. This is where helium comes from in the universe, guys. Helium comes from being constructed inside of a star. Did we talk about that part yesterday, about how atoms are made inside of stars? Briefly? All the atoms on this periodic table come from these fusion reactions happening inside of a star. This is where they're built. Okay? Stars can build everything up to number 26, Fe. Stars can't build atoms heavier than Fe because it costs more energy than the star produces in the reaction to go further than this. That's the sort of short, basic answer. We don't need to go into the long answer. To be honest, I'm not super great at the long answer. Stars can't build the stuff after this. It takes too much energy for the star. So here's a weird question. If hydrogen is the most common element in the universe, and the reason anything other than hydrogen exists is because stars are assembling those things, and stars can't assemble anything bigger than Fe, where the rest of the more than half the chart is after that. Supernova. We talked about that?
Yes.
Okay. High energy supernovas can build the rest of this stuff. Okay? Now think about this. The elements that make up your body, you're mostly made up of hydrogen and oxygen, but you've got a lot of carbon also, a whole bunch of carbon. Hydrogen, well, there's lots of that in the universe, but oxygen is number 8, carbon is number 6, and then you have nitrogen and all sorts of other stuff in you, calcium. Those atoms that are making up your physical body, without which you would not exist, were hammered together in the center of a star, and in some cases, if they're bigger ones, in a supernova. And you're made out of that stuff. And we're probably, everybody on this planet, are mostly made out of atoms that were all part of the same star at one time. Which is kind of an interesting connection to me between us. So, this is fusion. Happens in here, happens in the core of the sun. Real interesting, quick note, totally off topic, but since this picture's up here, I'm going to show you. It happens in the center, that's where the gravity's highest, okay? Light is produced from this reaction, okay? And then the photon takes off at the speed of light, but it does not go very far because here in the core of the sun, protons and neutrons are just like really close, almost as close as they get in the universe. So it immediately rams into another nucleus and then gets re-emitted in a random direction, okay? So these photons kind of play pinball. And they get further and further and further until they finally get outside and they get shot out of the sun and maybe fall on our planet Earth. Yes?
How would the elements from supernovas, how would they travel to our planet? Yeah.
Our planet is made out of them. Hold that question for just a second, I'll answer it, because this part's kind of cool. How long do you think it takes light that we estimate to get from here to here before it takes off at the speed of light? Remember, speed of light's really fast, 300 million meters per second.
Well, a couple years.
About 1 million is the estimate. Because it's ramming into stuff and then it's playing pinball in here for a long time. We think that the photons kick around for about, the mathematical estimates say about 1 million years before they finally make it to the surface and shoot off.
So it's basically like being ping pong this way, it's like slightly being ping pong back.
Just by random chance, eventually it migrates around until it finally makes its way out. On average, a photon will kick around in there for about 1 million years. So photons that land on the planet, the photons you see out there at the window right now, were kicking around in the sun for like 1 million years before they got free. Kind of crazy, right? Okay, so here's to answer your question. The universe is about 13.5 billion years old, according to current estimates. And those estimates change sometimes, and there's a long, kind of complicated way that people are calculating that. Okay? And that could change. This is why science works, things change. We're real sure, we have a lot of pretty strong evidence that our solar system is about 4.5 billion years old. So that means our solar system was not around until the universe was 9 billion years old. Okay? Remember, the four forces that we've talked about have been operating this whole time. Gravity, electromagnetic, strong nuclear, and weak nuclear. Forget about the strong and weak nuclear for now, we don't need to deal with those. But gravity, electromagnetism have been working, okay? And gravity pulls together big clouds of hydrogen. The hydrogens are all pulling on each other, and the more they're together, the more what they have. So the more mass they have, so the more what they have. This is all Unit 2 stuff. If you have more mass, you have more gravity. So the more they get together, the more hydrogens they pull together. And eventually they form these stars that are what? There are stars out there that make our sun look like a speck, yeah. Okay, there are stars, you remember the size of our solar system we were messing with. There are stars as big as our solar system. Close to. Yeah, there are humongous stars out there. So, enough that stuff collects together, all right? It builds up and builds up until it gets to iron. Same rules kind of apply for these stars. And the way we know this is by looking at them with telescopes and measuring the light. We can tell by something called spectroscopy, which we probably talked about yesterday. We can tell what kind of atoms are being forged in those stars. So we know they don't build bigger than iron. They might or might not. They may not have any planets. We're not sure. We don't know. We have a new way of telling if it turns out that a lot more stars have planets than scientists predicted early on. we kind of thought, well, maybe planets are kind of rare. But we've got a telescope now called Kepler that actually, you can't see a planet you can't see another planet from that far away. There's just not enough reflected light. But what you can see is when a planet goes across the surface of the sun, that sun dims a tiny bit, and that's actually measurable. So we actually have discovered planets, and we can tell how big they are by how much they dim the sun and how often they travel around their sun. Okay, so we know that. This giant star, back to answer your question, eventually explodes, okay, supernova. And when that happened, this would have happened before our solar system, right? All that stuff goes flying apart from each other, blown apart. Now eventually a bunch of it starts collecting back together, and a new star forms, and all the planets of our solar system form. So they're formed out of that stuff. Okay, so that's how it got here. We formed out of X star material. The whole planet formed out of that.
Okay, one moment, we need to interrupt. Chris Elliott, are you here?
That's okay.
Chris Elliott? All right, and Kevin, Castilla. There. There's Kevin. Okay. No Chris Elliott.
Thanks.
So here we are at states of matter. Ethan. Sorry? I don't know that term. It's probably a really big supernova would be my guess, but I don't know. That's one I haven't heard before. Is that a my guess would be extra large supernova, but I don't know.
Yeah, it's a
Bigger than usual supernova.
type of star explosion with an energy substantially higher than that of a standard supernova.
So, let's talk about states of matter. And be ready because you're going to have to get up out of your chairs in a minute. Yes, sir? Oh, can you turn? Okay. Yeah, physical. Okay, so, actually, pause for a second. Let's go back to chemical reactions for a second, because we did this demonstration in later classes, but didn't do it in here, so I would like to do it. In a nuclear reaction, does the atom change into a different kind of atom?
In a nuclear reaction?
In a nuclear reaction, do the atoms that start out end up changing into different kinds of atoms?
Yes.
Yes. Either they split, now they don't have the same number of protons, or they forge together, now they don't have the same number of protons. Okay? So in a nuclear reaction, the atoms are actually changing into other kinds of atoms. In a chemical reaction, do the atoms change into other kinds of atoms?
No.
No, because it only involves the what?
Electrons.
Okay, now, let's talk for a minute about what this looks like, okay? This is important, and it's super important to that kind of what molecular structure looks like, because you need to understand this part to get how it works. You remember I said that what we say is the number of protons equals the number of what?
Electrons.
Electrons. The reason we say that is because if I have a positive 1 charged proton at a hydrogen nucleus, if it has a +1 charge and along comes an electron, what's going to happen if they get close to each other? They attract. Opposite charges attract. So I have a +1 charge and I have a -1 charge. When we do +1 and -1, what do we end up with? 0. Now that atom has a 0 charge. Is it going to attract more electrons?
No.
Not electromagnetically. Okay? Here's what we're going to get into later today, hopefully, and definitely tomorrow. You will find out that beyond just trying to balance the charges, atoms follow this other rule. Okay? We call it the octet rule. Well, that's a little weird because the first layer only has 2. Because the way the orbits of electrons work, it turns out to be beneficial in terms of making the atom more stable if it has certain numbers of electrons. And that stability turns out to be more important in some cases than being magnetically neutral. Okay? So sometimes it is desirable, although atoms don't really have desires on their own, it is desirable for atoms to have different number of electrons and protons. And in fact, most of the time, this is the case, actually. So here's how it works. Hunter's an atom, and I'm an atom, and we're at a party. And let's say I have one proton, so I'm what? Hydrogen. Okay, so you would expect me to have one electron. I've arrived at the party with my one electron. Now Hunter is lithium. Okay, he has 3 protons. So how many electrons would you expect him to have?
3.
3. And he arrives at the party with his 3 electrons. It turns out that both of us would be much more stable in terms of these orbits if I had 2 electrons and if he had 2 electrons. Okay? So, can we help each other out?
Yes.
Yes, how?
Fusion. I combine.
It's not fusion, that's nuclear reaction. We're talking about chemical reactions. Well, he has one more than he needs, and I have one. Yeah, he could give me one of his electrons, right? So there are 2 ways this can happen, and this is not how it has. Both of them can't be true, but we're going to cover both of them for this theoretical lithium and hydrogen reaction, okay? Here's what happens. There are 2 ways this could happen. So in some way, I need his electron. He could just give me his electron, okay? In order for him to give me his electron, we have to get pretty close, right? So imagine what happens. He has a 0 charge, and I have a 0 charge. Hand me your electron. You need to get rid of it.
Oh.
No, your electron. Just imagining it.
Oh.
Okay, I think.
That's right.
Okay. Pretend this is worth a -1 charge, okay? What's his charge now? It's weird. This is why it would have been better if they had given electrons the positive charge. His charge is now, he has 3 protons, but he's given away one of his 3 electrons. So he has 3 protons and 2. He's +1 now, okay? I was 0. Now I have this -1 I'm carrying around. So what's my charge?
-1.
Ah, his charge is 1 plus and mine is 1 minus. What do?
Attract.
We're buddies now. We have just formed a what?
A pact.
The atom.
A molecule.
A molecule, yeah.
We are 2 atoms and we're bonded. Okay, we've just formed a molecule. We stuck together because of this charge difference. That's called an ionic bond.
So 2 more atoms put together to make a molecule?
Yes. Remember, letters are to words as atoms are to molecules. Okay? So we were just individual letters, we've just formed a word. Now get your electron charge out, because there's another way we can do this. The other thing we could have done is this. We have this problem. That's called an ionic bond, and it's called an ionic bond because an atom with a charge is called an ion. Okay? So we magnetically stuck together. And we're going to stick together until something better comes along, okay? And sometimes, actually, depends on how this reaction happened, but probably it's going to take some energy to get us apart, because we're buddies now. You're going to have to pry us apart. Now, the other thing that could happen is this. Instead of him giving me his electron, I could say, hey, dude, I need an electron. He's like, I need to get rid of this electron. And we could decide to share the electron. Pass it back and forth. And then the average is that we each get what? Charge. Or we each get what? How many electrons? 2 each, right? Half the time he has lost 1 and half. So it equals out. But in order to share it, we're what?
Giving it back and forth?
So we're attached, right? So that's a different kind of bond. It's called a covalent bond. Because the orbits of the electrons are called valence levels. You should write that down. And we are sharing an electron in one of our valence levels. Our final valence level, V-A-L-E-N-C-E. We're still a what now that we're stuck together? A molecule. Now we'll stay a molecule until what could happen is we go to another party later. Now we're a molecule. We hang together all the time, okay? And it can happen that certain events could turn out that it turns out to be better that we split up, okay? Hung out long enough. So I give him his electron back, and for whatever reason, I go join up. Oh man, see you later. I'm gonna go join these 3, and we're gonna do some trading of electrons, and now we're what? A molecule. Okay? So chemical change, in a chemical change, does the atom change?
No.
But does the molecule change?
Yes.
Yes, and something happens with the electrons, okay? So what happens in a physical change?
Nothing.
None of that. None of that. We might pull some, the party might split up, everybody goes home, but they go home the same way that they came to the party. Okay? Whatever molecules they were in when they got there. Okay? So a physical change doesn't involve any of those parts. It doesn't even alter the molecules themselves. Now, have I come up with a way for you to remember that was better than the one you learned in middle school? It might be more complicated, I don't know. When thinking about a physical change, if I draw on this paper, right, this is a thing you would always do. You take a crayon and rub it on the paper, and they'd say, is that a chemical change or a physical change? Well, what do you think? Chemical or physical?
Physical.
Did any electrons change places?
No.
No. I just rubbed some of the molecules away from this party and sent them to that party, but they're still the same molecules of graphite. Okay? None of the molecules of the paper changed. If I burn the paper, do you think that the molecules are all the same as they were before?
No.
No. So chemical change, physical change, or nuclear?
Chemical.
Chemical. Electrons change places in that burning. That's the party, the fire. Okay? Now, state change. Going from ice to liquid, hot solid to liquid to gas. That cloud is actually lots of little tiny drops of liquid, but there is gas out here in the atmosphere. There's water in the gaseous form out here, I promise you. And then plasma we'll leave alone for the moment. It does happen, but it's a little less important to us right now. Do you think a state change is a nuclear change, a chemical change, or a physical change? When you go from a solid to a liquid to a gas, or vice versa?
Physical.
Who said physical? Why do you think physical? You don't think electrons change places?
Because like, I don't know, I just think it's physical.
Okay. Do you think that when water goes from a solid to a liquid that the electrons change places? And that the molecules change? Miguel's nodding. Stick to your guns! It's a physical change. You're right. Come on. Just because I try to talk
Can I
about
say
it.
why I think why was probably wrong?
No.
Yeah, tell me.
Okay, because water is a liquid, so like if you change it to ice, it can become a liquid again.
That's correct. Let me ask you this. If you change it to ice, is it still water molecules?
Yes.
Yes. If you change it to a gas, is it still water molecules?
Yes.
Yes. They are all at the party. Okay? They haven't traded partners. Oh, why is it so easy for me to talk you guys out of this stuff? Okay. Stand up. Because this is a thing.
Oh, see that house
Start
walks
doing
in, you
years
don't
ago
stand up.
to show physical
It's the right kind of
state change.
respect, that's what I'm saying.
I guess we're all.
Yeah, knock this house.
Everybody
Okay.
just turns their faces away when I walk in.
State changes. These don't have to do with changing the molecules. It has to do with how much energy, and we call this type of energy heat energy, how much energy the molecules have. Now, pretty much heat is really a measure of how much total vibration there is in all the molecules in the system. Well, the molecules bump into each other and lose some of their energy to friction, and that's what you feel as heat. Okay? People talk about, well, what about cold energy? Cold is just the lack of vibration. Okay, so there's no such thing as cold energy. That's just you're just noticing there's a lack of heat. Okay? Now,
I have a question.
yeah,
So was like a heat wave just like a large energy wave?
a heat wave? You mean like when they say we got a heat wave?
Yeah.
It's just a bunch of, usually it's just a bunch of hot air moving through an area that's carrying all the heat in the air. And it's transferred to you. This is about to make a whole lot more sense, I know. Okay? We got 3 energy states, and look at me, because you're going to be doing this in a minute. Well, we're going to skip plasma now. In a solid state, there's actually still a little motion in the particles, but this is it. Give me some of this. This is a solid state. Okay, give me some of
It's like
this.
an awkward middle school dance.
Yeah, it's like an awkward middle school dance.
Like an awkward
Give me some of that
today.
parties.
And Clay, do me a favor and join a table. Join a table with more people for a minute. Okay.
Stand next to me,
Yeah,
Clay.
join a table with more people for a minute. So this is a solid. Okay? Now, there's some energy in there, right? The molecules are moving. All right? If you get to zero motion of the molecule, you've reached a temperature we call what? Anybody? Absolute zero. No energy. Okay? There's always some motion, okay? Now, liquid is a different state. Liquid is kind of, it can flow. So walk around each other, but stick close to each other, okay? Because usually liquids are kind of sticking close to each other. They're like, you're a little more, okay? Just a little more. Now let me ask you a question. Pause. Turn back into a solid for a minute. Okay? Turn back into a solid for a minute. In which way do you need more space? As a solid or as a liquid?
Liquid.
Yeah, you take a little more space, right?
Yep.
Okay. Now, liquids are interesting. Be liquids again, because there's enough motion that I could go over there. I can separate them and put them back together with other liquids, okay? Hold on, divert you that direction. Okay. Pause for a minute, turn back into a solid for a minute. Okay, so in a liquid, the molecules can be separated. In a solid, it's harder. They can be separated too. You've got to do more work to get them apart because they're closer, okay? Their attraction is a little higher, okay? Now, here's a gas.
Yeah!
All right? So, give me a gas. All right? And you don't even have to stay near each other now. In fact, you're going to go all over the room. You're going to take up as much space as you can. You're much better than a gas. Come on, you're being solid. Give me a gas. Everybody, give me some gas. When you hit each other, you just kind of bounce around. Okay, go back to solid. Go back to solid. Take the energy out of you. Slow down. Now, which one of these states takes up the most space? Gas. You got a lot of energy, you got to move around, okay? And the funny thing about gases is they don't even, like liquids will hang out together, like, yo, what's up? Walk around together. Gases don't even do that. They got so much energy, they're just like all over the place crazy, okay? Solids are like, yo, what's up? We're together. What's up? Okay? LAC. I told you were going to be up here. So, each of us was pretending to be a molecule right then, not just an atom. Okay? When you take enough energy out and you get down to solid,